It was several weeks before an immigrant from Earth could adapt to it. On the Moon, the human body had to learn a whole new set of reflexes. It had, for the first time, to distinguish between mass and weight. A man who weighed 180 pounds on Earth might be delighted to discover that he weighed only 30 pounds on the Moon. As long as he moved in a straight line at a uniform speed, he felt a wonderful sense of buoyancy. But as soon as he attempted to change course, to turn corners, or to stop suddenly, then he would find that his full 180 pounds of mass, or inertia, was still there. For that was fixed and unalterable, the same on Earth, Moon, Sun, or in free space. Before one could be properly adapted to lunar living, therefore, it was essential to learn that all objects were now 6 times as sluggish as their mere weight would suggest. It was a lesson usually driven home by numerous collisions and hard knocks, and old lunar hands kept their distance from newcomers until they were acclimatized. From Arthur C. Clarke's 2001, A Space Odyssey. In the lab, you found the mass of 6 objects. You then weighed the objects on a scale calibrated in newtons. A newton is a derived unit which measures force. A derived unit is made up of other units. A newton is equal to 1 kilogram meter per second squared. Graphing the weight in newtons versus the mass in kilograms, you should have developed something that looks like this, showing a directly proportional relationship between weight and mass. You were then asked to do a 4-step analysis of your graph. In step 1, you were to write the basic equation of a line, y equals mx plus b. In step 2, you were to substitute your variables from the graph. From your y-axis, you had the weight, and from your x-axis, you had the mass. Since we already have an m in the basic equation, then I went ahead and wrote out mass. In step 3, you were to replace the constants, which requires you to find the slope and the y-intercept. The y-intercept is easy. It was 0. To find your slope, well, you know how to do that. Just rise over run. And so our slope came out 9.79 meters per second squared. Step 4, simplify and form a general equation. Our general equation said that the weight is equal to mass times 9.8. That 9.8 is a constant. Look at that. You just found out where that value, 9.8 meters per second for gravitational acceleration, comes from. An object's weight on Earth is always equal to its mass times 9.8 meters per second squared. The quote at the beginning of this presentation contrasts mass and weight. On the Moon, your inertia would stay the same because your mass is the same. Your weight would be 1/6 of what it is on Earth. Think about what an adjustment that would require. Be ready to discuss it in class tomorrow.